few things to say before starting back into material. I have assigned the 5th problem set. It's a long one, but it'll count the same as, ultimately it will have the same overall weighting as a typical problem set, even though it's a last 23 questions long. It's a retro problem set in that, the last problem set I assigned included material too far along, really. I'm still working on it. And so rather than try to give you another problem set just like it, I'm going to go backwards a little bit and give you a problem set that's to an extent review, but from talking to people in office hours and otherwise, it won't do you any harm. It's useful to work through these same problems. So it's up there. I'm realizing you're not all getting the solutions, I think, for the problems. I'll post. I have discussions of each of the questions. I'll put them up for the problem set that passed, and when this problem set's over, I'll put those up too. I thought I had them coded in properly to Colab, but they're not showing up as far as I can tell. So sorry about that. All right. Reminder that the second midterm is a week from Monday, as I recall. Okay. The 24th, I think. All right. So water distribution, where I want to sort of finish up with water distribution is to make sure that you understand what's known as Bernoulli's equation and the conceptual story underlying it. The basic idea is that in certain contexts, you can use the fact that energy is conserved to watch energy within a flow of water or another liquid, and gases too, although gases are a little more complicated because you can compress a gas. But you can watch the energy in the flow of liquid move from one form to another. And that becomes very useful in sort of understanding how the flow itself works. So the context in which Bernoulli's equation works particularly well is one that's known as steady state flow, a word I never used in class yet. So here it is. Steady state flow is the flow of a liquid through a system where you can't see anything changing with time, so that a movie of the flow looks just like a photograph of the flow. What's an example? Well, not example, but what does that require then? First off, the environment around the flow, the plumbing, can't move. And what else? The flow has to keep on going. It has to start sort of out of your view, come through, and continue out beyond your view. So actually, you don't need to worry about the flow going off forever, coming from wherever and going wherever. Concentrate on an area. And if you find an area in which the environment is not moving, the flow is passing through it smoothly, and you can't see the evolution of time, it's steady state flow. So when you first open a faucet, for example, that's not steady state flow because the water's starting, you can watch it go by. You can watch the leading edge go by. When you turn off the flow, same thing, not steady state flow. But when you turn on the flow and wait a little while, it evolves into steady state flow. Then you're good. Any questions about the concept of steady state flow? Why no moving environment? If the environment moves, it can do work or negative work on the fluid. That's not allowed. That's going to mess up the steadiness of energy. And as to why you have to have the flow itself continuing smoothly, that's also an energy issue. The leading edge and the tailing edge, it gets messy. Okay, so in that context of this steady flow through a stationary environment, you can watch droplets move through the system, followed by identical droplets moving through the system. You get a whole, if you follow basically one droplet, put ink in it, and watch that thing move through the plumbing. It goes up and down. It might speed up and slow down. Whatever. It maps out a line, not a straight one, but it wends its way through the system. And that line is called the streamline, just to give it a name. And there are many streamlines in a typical steady state flow, because if you put a drop in, say here, it follows a path. The drop here never follows that same path. It follows a different path. Each one maps out its own streamline. So you typically, the way I've got drawings, I don't have one here to show you, but in a drawing, you'll see a whole series of lines. never touching one another, never crossing one another, because each one's got a different story to tell. Those streamlines are very useful. And Bernoulli's equation describes what happens along one of those streamlines. In fact, or each one individually. And that is that the total ordered energy of a drop along that streamline never changes. As long as, in this steady state flow, the drop can work its way through. It can go up and down. It can speed up. It can slow down. Its pressure can rise and fall. But if you sum up its total energy, which has three possible forms, pressure potential energy, kinetic energy, and gravitational potential energy, that sum will be the same all the way through the steady state flow along that streamline. You okay? Questions about that? That's leading confusion to you. So picture a nice smooth flow. For example, the water flowing in a slow river. So no swirling white water. Just a gentle, lazy flow along. If you put drops of ink at the same spot, second after second after second, you'll see the drops work their way through the system along the same streamline, because they all share the same history. They passed right under the dropper, and they all follow that same path. If you watch the water along that path, it may go up and down, it may speed up, slow down, its pressure may rise and fall, but if you sum the energy, it'll be the same. Any questions about that idea? Yeah. So the question is a nice example of this, a lazy river that you see at a water park. Yes. So no swirling, and don't put people in it, because the people will move, and that will change things. But as long as the river walls don't move, they cheat. They blow water in those lazy rivers in the amusement parks. But basically, along it goes, nice and smooth. Is that okay? Yeah. Yes, if they're on the same streamline, then the drops are equivalent. One is earlier than the other. If you're watching, so here's a drop that was dropped in just now, and here's a drop over here that used to be that drop, but has now worked its way to here. Those two drops are distinguished only by what time it is. They're otherwise identical, because this one used to be right where that current one is. Those drops all share the same, they have the same energy per drop. And so that we can compare them. All right? If you take two drops that are not on the same streamline, they don't have the same history. They were never equivalent. And you can't be sure they have the same total energy. They might, but they might not. And so don't try to compare them. And you'll see that there are various truisms floating around. The most important or most famous one is that fast-moving air is low-pressure air. This just sort of is a truism that shows up in not quite everyday speech. I haven't seen it in the debates yet, but it's misleading, because it's sometimes true, but not always. Fast-moving air is low-pressure air. Well, what if you take a canister, a scuba tank full of high-pressure air and drop it out of a plane? It's going to be very fast-moving air that is very high-pressure air. So there's a counterexample. It will turn out, though, if you have air that's flowing through a system that causes it to speed up, and it's steady-state flow, it's on a streamline, and it speeds up, its pressure will decrease. So that's where the truism comes from, but it's not generally true. All right? So that then leads me to examples of steady-state flow in which somehow the system causes the flow to exchange energy between these three forms. So you've got pressure potential energy, that's one form. Kinetics another. Gravitational is a third. There should be, and in fact are, ways to force one energy to become the other energy in the flow. And so there's 6 possible exchanges. You've got three starting points, 3 ending points that are, well, 2 that are different. So that's 3 times 2 is 6. There's six simple transformations to convert, for example, gravitational to kinetic, or gravitational to pressure, and so on. So let me show you those, and ask me if any of them are confusing. So the first one is, the first pair is how you force water to convert pressure potential energy to gravitational potential energy, or back again, one or the other. Okay, so this is to do it purely. If you send water through a uniform pipe, uniform meaning that it's got a steady cross section to it. It's cylindrical. It doesn't bulge out and bulge in, funny stuff. If you send water through a pipe like that, the water can't speed up or slow down without causing trouble to the water. If the water slows down partway through the pipe, it sort of backs up. There's a bottleneck. And the water behind crashes into the water in front. That can't happen. And if the water speeds up going through that uniform pipe, it'll leave a gap behind it. So that can't happen either. So water flowing through a uniform pipe can't change its speed. Are you okay with that idea? If not, ask me. I mean, my usual analogy is like on a highway where you got bumper-to-bumper traffic. Water's like bumper-to-bumper traffic. Every car is touching every car. In fact, the water molecules are all touching one another. You can't squish them tighter. You can't unsquish them. They're packed at a certain tightness. And similarly, cars bumper-to-bumper on a highway are packed at a certain tightness. You can't have, along this uniform highway, it's 3 lanes the whole way. You can't have cars entering the highway driving twice as fast as cars halfway down the highway. You'll have collisions. Similarly, you can't have cars speeding up. It won't be bumper to bumper pretty soon. Cars at the front will just pull away. So, uniform pipes, steady speed. In that case, the kinetic energy is stuck. Whatever it is entering the pipe, it's the same coming out of the pipe, because kinetic energy depends on speed. So, uniform pipes can allow water to exchange its energy between the other 2 choices, not kinetic energy. If the pipe goes up, a uniform pipe going up, and water's flowing up that pipe, it's converting pressure potential energy into gravitational potential energy. The water goes up and has more gravitational, but that costs something. The pressure drops. So water rising up in a skyscraper pipe, straight up in a uniform pipe, loses pressure, gains gravitational potential energy. That's why the pressure way up high is low. So far, so good? Do the reverse. Send the water down a pipe that's uniform. Now it loses gravitational potential energy as it descends, but gains pressure potential energy. This is the basis for a water tower. You put the water way up high, it's packed full of gravitational potential energy, and as it descends through the pipes to go feed the houses, its pressure increases. So the water tower pressurizes the water for you. Make sure that everybody's getting nice high pressure. It's a wonderful energy storage device. You can fill a water tower in the middle of the night when energy is relatively inexpensive, and now it's chock full of energy. It can handle your water system for you. So that's first pair of transformations. Hopefully they're pretty straightforward. Second pair, if you spray water, a stream of water, through the open air, its pressure is fixed at atmospheric pressure. It can't be higher or lower when it's out in the open. If it were higher than atmospheric pressure, it would accelerate towards atmosphere and would spread out. If it were lower than atmospheric pressure, the air would crush inward and build this pressure back up. So an open air stream of water is at atmospheric pressure, the ambient pressure around it. Okay, so open air sprays then have fixed pressure potential energy. It's the pressure potential energy associated with atmospheric pressure. Can't go up or down. So with that fixed, you can only exchange energy between gravitational potential and kinetic. Those are the only 2 that are free to roam. And so if you spray the water up, like out of a fountain, as it rises, it loses kinetic energy and gains gravitational potential energy. So fountains get slower as they go higher. You've watched this, right? They eventually stop rising. They stop rising when they run out of kinetic energy. they can't go any higher because they've got no more kinetic energy to turn into gravitational potential energy. Then, after that's over, they come back down. The water then descends. And as it descends in the open air, it converts gravitational potential energy into kinetic energy. It goes faster and faster. Is that okay? We can play with this. I'll bring back the tank over here again. We'll watch all the transformations are there. That's the second pair. We're on to the third pair. The last pair we've got to work with is to convert pressure potential energy into kinetic energy. So to keep the third energy constant, that is gravitational potential energy, work horizontally. Don't allow the water to rise or to go up or down in height. It can't change its gravitational potential energy. That's stuck now. So the only pair that can exchange is pressure potential energy and kinetic energy. And nozzles and anti-nozzles, what are known as diffusers, do these tricks. A nozzle is a passage where the flow going into the nozzle is wide, and then as the nozzle progresses, the flow necks down. And as it necks down, it has to speed up to prevent the equivalent of a traffic jam again. If you've got a 12-lane highway with bumper-to-bumper traffic on it, it might be moving very slowly. But if it comes down to a single lane, the traffic's going to go much faster in that single lane than it did in the 12 lanes. Because you've got to get the same number of cars through a single lane, they've got to be moving faster. Can you follow that? Is that okay? The idea that as you neck down a flow through a nozzle, that's what a nozzle is it's a necking down of the flow, steady state flow in this case. The flow has to speed up. Well, the flow going through the nozzle does speed up, but this costs something. It costs energy. And the energy comes out of pressure potential energy. So as water flows through a nozzle horizontally to get rid of any worries about gravitational potential energy, the flow experiences a drop in pressure and a rise in speed. It's converting pressure potential energy to kinetic energy. And a typical nozzle opens into the open air. The water comes out at atmospheric pressure. So it enters the nozzle at very high pressure. I don't know, whatever your water pressure is, way above atmosphere. And by the time it leaves the nozzle, the pressure is plummeted to atmospheric pressure. And in exchange, it's picked up a lot of kinetic energy. It's moving fast. So this is all the nozzles you've encountered, including shower heads and stuff like that. All right? It leaves one more possibility, and that is for a flow to convert its kinetic energy into pressure potential energy. And this happens in what's known as a diffuser. And then diffusers might be familiar to some of you as a component you stick on the end of your hair dryer. And that is a correct use of a diffuser. The diffuser necks out. It takes a flow that's moving at high speed and spreads it out. And as it spreads out, it slows down because it's now got more cross-section to go through. So it's going slower now. Well, if it's slowed down, it doesn't have as much kinetic energy. Where did the energy go? It goes into pressure potential energy. The pressure actually rises. An example of this is if you take a stream of water and shoot it against the wall, or put your hand, I'll shoot it, you put your hand there where it hits the wall, you'll feel it push hard on your hand. It's pushing with what? With pressure. That's high pressure water. When it hits your hand, and it's actually spreading out and slowing down. And as it does, it loses kinetic energy and it gains pressure potential energy. That is really high pressure air. In that case, there's no visible diffuser, but there is the effect of the diffuser. In a diffuser that you're familiar with, which is the one that sits on the hair dryer, the air is high speed inside the hair dryer, and it comes out, goes in the diffuser, it slows down, and its pressure rises. And the air, oddly enough, comes out at atmospheric pressure. And then you say, but I said that the pressure rises. Yeah, it rises up to atmospheric pressure. It actually went through your hairdryer below atmospheric pressure, which is okay. It's in a shielded environment. And in the neck of your hairdryer, heading to the diffuser, the pressure inside, if you snuck in and looked, it's actually below atmospheric pressure. And so the air is high speed, below atmospheric pressure. It goes through the diffuser, spreads out, and its pressure rises to atmospheric, and it comes out slowly, which is the desired effect of a diffuser. I mean, if you don't want your hair to be like blown out there like that, like some, it's a style, I suppose. If you want a gentle breeze blowing on you rather than a hurricane, you want to have the air convert its kinetic energy to pressure potential energy and sneak out and blow your hair gently. Okay, so that's the sixth transformation, flow through a diffuser. So all of them, just sort of get the job done here, you're all visible in this little pipe. Oops. So I'm gonna invest the energy. There, I did it. I did work lifting it up. The energy's packed in there. It's all gravitational right now. As the water descends through a uniform pipe, it converts its which energy to which energy? You can think about it. Gravitational to pressure potential. So it reaches peak pressure potential energy right here. If you snuck inside there, your ears would pop. Ooh, high pressure. Ooh, ooh. Okay? Yeah, and you have to do the ooh, ooh, too. As it rises back up here through a uniform pipe, its pressure decreases and its gravitational potential energy increases. So we did both of the first pair of transformations. The second pair of transformations is occurring now. I'll stop it, though. On the way up, it's converting kinetic energy to gravitational. On the way down, it was converting gravitational to kinetic. Second pair of transformations. And the third pair of transformations, I'm going to rotate this guy. Come on, rotate. That nozzle is taking high pressure water behind it, pressurized by this descent, and converting it to kinetic. Psh, there it is. Okay. Psh. So it went from slow moving high pressure to fast moving atmospheric pressure. And lastly, when it hits the table, right there, it's kind of messed up because it's not perfectly steady state flow because it's got droplets forming. But when it hits, the pressure surges upward and it converts kinetic energy into pressure potential energy. There's effectively a diffuser there. Is that okay? I'll take the energy back out. I need it. Short on energy today. Not really. I don't know what I'm talking about. Okay, so that's all the energy transformations that are possible in steady state flow. Have a stationary environment and let the flow go through so you can't see the change in the evolution of time. You can watch these energy transformations take place. Next time you're taking a shower, the energy, why is the water moving fast? Well, it was high pressure inside the nozzle. It's low pressure atmospheric outside, but it's converted pressure potential energy into kinetic, and so on. All right? That's enough for water distribution. Now we'll do garden watering. In the story of garden watering, it's the first, up until this point, we've sort of watched fluids moving around sort of we've assumed various perfections in the fluid, like it can't waste any energy as it moves through the plumbing. We've watched steady state flow, which is the simplest possible flow, and not all flow is steady state by any means. So now we're going to start to introduce some of the complications that show up in real fluids, and the fact that fluids have sort of a life of their own. And so my first fun and games with this is we got a smoke generator back here. If I press this button, this is a device that traps air inside here, and I've got a spring-mounted surface that hits the back. And something interesting comes out of this hole. And so that you can see that something interesting, I'll use a smoke generator. Oh, we can do better than that. That's better. Can you see the rings? They're going really slow. I'm used to having them just buzz across and blast people. So something's been modified in the past. What? So this is basically a smoke ring blower. These are actually called, they're often called vortices. So this is a vortex cannon. And if I bring it up closer, along with stinking, I'll make it. You can feel them when they hit you. So you can play. It's weird that it's changed so much. Anyway, what's happening is the air as it's coming out of that hole rubs against the hole basically, and it twirls this way. So it creates a ring that's twirling with the middle going faster than the forward, and the edges going backward. And this rotating thing self-sustains and crawls forward as a ring. So it's a vortex ring. Is it okay? You can play with it after class. It's usually I could shoot people across the room, but not today. All right. Question to start with then. You've all had this experience that if you take a hose or well, let's just stick with a garden hose. If you open the faucet and just take the hose, the water comes out relatively gently. But if you put your thumb over that same opening without changing anything else, a moment later, psst, the water starts spraying like crazy out the end. This effect. Rather than talk about it, I can do it, right? So there's the water coming gently out of the hose. I can go even quite gently. But if I put my hand over it, I can spray all across the room. Get everybody wet. So the question is, in which of those two circumstances does more water come out of the hose per second? You okay with the question? How many think that more water comes out of the hose when the hose end is uncovered? How many think more water comes out of the hose when the hose end is covered? Okay, the voting's thin, but the majority are going for the hose end uncovered. And that actually is the right answer. I mean, I'm giving away all my questions these days. It's the fact that you slow the flow down in the hose so that less water comes through when you put your thumb on it. Slowing the flow down is what allows the energy of the flow, the energy per drop, to be saved against losses and remain there right until the last moment when the water sprays out at high speed through what is basically a nozzle you make with your thumb. So the fact that less water comes through the hose when you cover the end with a thumb, and the fact that the water sprays like crazy when you cover the hose with a thumb, those go hand in hand. Slowing down the flow allows it to save its energy well and spray like crazy. Okay? Yeah, explain it again. When you put your thumb over the flow, you slow it down everywhere, all the way back to the water company. The water now is walking through the hose very slowly, and it turns out that the slower the flow is through the hose, the less it wastes its energy rubbing against things. We'll see that water actually does rub as it goes through things. It experiences something related to friction. So slow it down. When you slow it down, it doesn't rub as badly. That distinguishes it from friction, but it's true. And the result is that the water gets to the end, right where you spray it, packed full of ordered energy you can use. If you take your thumb off, the water goes faster, it rubs worse, it wastes more energy, and it comes out not with, instead of having the ordered energy it needs to leap off at high speed, it shows up with thermal energy, which isn't nearly as fun or interesting. All right? So that's part of the story for today then, is to deal with the imperfections of water flow. The steady state flow story I just told you 10 minutes ago assumes perfect flow, what's called eviscid flow. Don't write that word down. Flow without viscosity, no syrupiness to the water, and therefore no waste of energy. Now we're going to bring in the waste. So how does a faucet control flow? And part of that is that it's all about energy, I guess, is really the story. When you open a faucet, so one of the first questions is, before you open the faucet, where is the water? You know, is it back at the water company? Is it right there at the faucet waiting to get through? And the answer is it's right there at the faucet waiting to get through. There's pressurized water right there at the sealing surface in the faucet. There's a place in the faucet where the water sits, blocked from further progress by some surface that you're going to move when you open the faucet. So there's the water there waiting. When you open the faucet, what you're doing is you're providing a path, small at first, potentially larger later, you know, as you turn the knob further, through which the water can flow. And so you might think, well, why doesn't all the water in the world flow through that hole in 1 second? Well, there are at least two reasons for it. The first we already know, and that is that the energy's only got so much energy per drop. It's not exactly steady state flow, but the ideas still work out okay. And that is that the water company provides a certain amount of energy per drop, which shows up as pressure, potential energy, or gravitational potential energy, or kinetic energy. And in going through that opening that you make when you open the faucet, the fastest the water can flow through it is having turned all of its available energy into kinetic. It can't go any faster. It doesn't have any more energy per drop to go faster. So if the water can only go 100 miles an hour max speed, and it's going through a hole that's this big around, you can only push so much water. Picture a cylinder of water that's rushing through at 100 miles an hour. There's not a billion gallons of water in that. It's a certain amount every second. That's all there is. That's all you use. So the size of that opening and the maximum speed of the water determine how much water can go through the water. The maximum speed of the water, determined by energy, determines how much water can get through that hole every second. The bigger the hole, the more water can go through, even if it has the same speed. So that gives you the origin of the flow control in a faucet. Questions about that idea? There's a second piece to the story, and that is that even the water can't even go through that fast. It doesn't even, not even that much water can go through. Why? Because the water rubs on all the surfaces as it goes through, and this sucks energy out of the flow. It wastes, does negative work on the fluid and wastes its energy, so that you don't even get full speed in the flow. You get less than that. And the origins of that reduction in flow, there are two of them. One of them is what's known as viscosity. The water, like all fluids, has a syrupiness to it. And that means in a syrup, or honey, if you will, you can have a big pool of honey. No, not fun for swimming, but okay, there it is. And yeah, the fluid can rub against the wall itself, and that's effectively a friction effect. But the fluid can rub up against the fluid. If you try to get this portion of fluid moving forward, and that portion of fluid you want it to sit still, it won't happen. Moving this portion forward will cause that portion to get drawn along with it, because the fluid rubs against itself. And that rubbing of a fluid against itself, when portions of it are in relative motion, is called viscosity. So viscous, hopefully it's just a familiar term to you. A highly viscous fluid would be something like honey or molasses, or some kinds of oils. A fluid with low viscosity would be something like water, or even lower would be something like air. Air has viscosity too. It's very small, but not zero. So when I move this portion of air forward, the portions around it, no, they rub against each other. Is that okay? So that's one reason, one effect that limits the flow of water through the faucet. The other is turbulence. And so up until now, I've looked at the flow as though it was perfect. It has these lovely little streamlines running through it where you follow a drop and off it goes. But that's not the only way fluids can flow. They can also tumble and have swirling eddies and stuff in the vortices in them. And picture white water on a instead of a lazy river, picture the New River Valley, the rafting trips. The water's all bouncing around. That's called turbulence. And
Turbulence wastes ordered energy like crazy. So it turns the sum of gravitational plus pressure plus kinetic, it just turns it into a mush and thermal energy very rapidly. So you get viscous effects and you get turbulent effects in faucets, and that slows down the water flow. This is basically what I just said about viscosity, that viscous forces oppose relative motion within a fluid. So if you try to get water flowing on one side and not flowing on the other, they talk to each other, they rub. And that viscous forces waste energy as thermal energy. They waste ordered energy. Different fluids have different viscosities. It's into the chemistry of the fluid. Okay? Any questions about viscosity in general, the basic idea? I mean, the world of fluid flow and with viscosity and everything, the story can get so complicated that it remains a matter of modern research even after hundreds of years of people studying fluid flow. So these are, the details are very complicated. The general picture is you know that fluids have trouble moving sometimes, like pouring honey out of a pot. It's slow. It's got plenty of energy in the form of gravitation once you lift the bottle up and turn it over, but that doesn't get the motion going very fast because it's rubbing like crazy against itself and ultimately against the walls of the pot. All right. So this then leads to the well, the question is how much flow, how does the diameter of a hose matter? And the answer is it matters an astonishingly large amount. So what? The flow through a hose is, if you turn it on and let it go into steady state flow, there's no turbulence, everything looks great, but the flow is limited. And just to sort of set the stage, if there were no viscosity around, that is, the fluid did not rub against itself at all, you could, in principle, get a cylinder of water started in a garden hose that was 100 miles long, and that cylinder of water would just coast. It's got inertia. It's got mass. If it was moving, it'll keep moving. It would go all the way through the 100 miles of hose and come out the other end. Woo! It might take a while, but it would get there. That doesn't happen. The reason it doesn't happen is because the water rubs. The outermost layer of water in this cylinder going through the hose actually touches the hose. And that water doesn't move. When people have studied this has been a sort of question of complicated question to deal with. Is that water really stationary? And the answer appears to be yes, it's not moving. There is a layer of water, it might be only a couple of atoms thick, that doesn't move at all. Okay? The layer just inside that layer rubs against the stationary layer by way of viscous effects, viscous forces, the forces between moving portions of fluid. So it rubs, it's very aware of the wall, not because it's touching the wall, but because it's touching the water that's touching the wall. And the layer that's inside that rubs against this previous layer, and it's a whole series. Even the water at the center of the hose is aware of the walls of the hose because it rubs against a layer that rubs against a layer that rubs against a layer, and so on, all the way to the wall. The thickness of the layers doesn't matter. You just sort of picture an onion, peeling an onion. It's like peeling an onion of cylinders going all the way from the center of the hose to the edges. The result of this rubbing effect is that water doesn't coast through a hose. You have to push it the whole way, just like you have to drag a log across the ground. Friction's going to pull back. You have to pull equally hard the other way. Right? So to keep it going at steady speed, constant velocity. So if you want water to go at constant velocity through a hose, you got to push. How do you push? With a difference in pressure between the entry and the exit. Higher pressure at the start, lower pressure at the end. And that imbalance in pressure pushes the water through. Okay? So you need a pressure imbalance. The question is, for a given pressure imbalance, how much water gets through the hose? It turns out it depends on four things. So there are my four things. It depends on the pressure difference. If you double the pressure difference, you pump up higher on the entry, more water will go through. You're pushing harder, you'll keep it going at higher speed. Incidentally, viscous forces do depend on speed. So the faster you make the water move, and the faster you make these layers slide across one another, the harder they push back, the more they fight it. That's different from friction, which doesn't really depend on speed very much, sliding friction. So the point at this point is you crank up the pressure difference, pump harder, you get more fluid through it. It's pretty much proportional. Double the pressure difference, you double the water flow. The hose length matters because the longer the hose is, the more the water rubs. You've got a longer cylinder of water rubbing its way through a hose. So you double the length of the hose, you got twice as the flow goes down by a factor of 2 if you have a double length hose, unless you compensate. Third thing is viscosity matters. The more syrupy the water is, the more the layers talk to each other, and the slower they go, the more they notice that the edge of the hose is present. And viscosity is defined as increasing. The bigger the viscosity, it's actually a number characterizing the fluid. The larger that viscosity, the syrupier the stuff is. So honey has a big viscosity, water a small one, air a very, very small one. So if you take 1 over the viscosity, that sort of gives you a pretty good measure of how much water you're going to get through the hose. Water's got a viscosity. I don't know it offhand. It doesn't matter. But you don't have much control over that. That's water. Okay. Last thing to affect the flow of water through a hose, the hose diameter. But not just doubling the hose diameter doesn't just double the water flow. It increases the water flow by a factor of 16. It turns out that the water flow through a hose is proportional to the 4th power of the diameter of the hose. Now, why is that? The reason it's 4th power is two parts. The first part is if you double the diameter of the hose, the cross-sectional area through which the water is flowing goes up by a factor of 2. Remember the slice through the circle that you get when you slice through a hose is its area is pi r squared, right? So r squared or pi over 4 diameter squared, if you like. So doubling the diameter gives you 4 times as much cross section to go through. So the hose, without much change, can carry 4 times as much water every second because there's just a bigger opening to go through. The other effect is when you double the diameter of the hose, you move the water at the center of the hose twice as far away from the walls. And actually the walls in both sort of two directions at right angles. It makes a big effect. That water at the center becomes a lot freer to move when you double the diameter of the hose. So when you do all the calculations carefully, it turns out that the water that goes through a hose depends on the 4th power of the diameter of the hose. So doubling it allows it to carry 16 times as much water for the same pressure difference, the same water, so the same viscosity, and the same length of hose. I can show you approximately this effect. I remember to, and again, remind me to, where's it? Remember to undo this change over here. So here's a tank of water that will provide us with a specifically pressurized water. So we'll have this pressure right here, based on how high that water is. And we're going to let water go through it. And this is a little capillary. The water is, I got to pull this out. Oh. The water is just dripping out here. You see that? So this is 1 unit of diameter. I'm going to go to twice the diameter. Ready? So there's twice the diameter. And I hope you can see the water's coming out much faster. You know, something on the order of 16 times as fast just by doubling the diameter of the hose. And before I forget, press the button. So public service story here. When you go to the garden store or the hardware store and you buy hoses, the two classic diameters of hoses in the United States are 5/8 inch and 3/4 inch. So 5/8, 3/4, that's not very much difference. 5/8 versus 6/8, big deal. Yeah, it's a big deal. One will carry twice as much water, all else being equal, than the other. Just increasing from 5/8 to 3/4. That little change in diameter, when you raise it to the 4th power, doubles the amount of water the hose can carry for the same pressure difference, same length, same viscosity in water. So it matters. Next time you go shopping, one of these days you might want to buy a hose, and you go, oh, no difference, but this one costs $4 more. That might be a good, well-spent $4. If you're trying to fill a pool, for example, it's a big difference. Twice, it's 2 days instead of 4 days. All right? This also explains why blood flow in our bodies depends very critically on the accumulation of plaques and stuff on the plumbing. Our plumbing gradually degrades, or house plumbing gradually degrades. Same thing, it accumulates minerals in your house plumbing. It doesn't take a very large change in the diameter of the hose to dramatically change how much water or blood it can carry. So pay attention. All right? The factor, people ask me about the factor that up here, this pi over 128. That's when you do the calculation carefully. I can't control it. It is what it is. Let me see if I can give you anything more that's worth doing before we call it a day here. Let me talk about that question, the open hose question. Just let me return to it, just to show you. When you let the water flow through the hose unobstructed, it moves relatively fast through the hose. It's rubbing the whole way, and it's using the whole pressure difference between whatever the water company provides it with, high pressure and atmospheric pressure. That whole difference is being used to make the flow go through the hose, and it's limited by the diameter of the hose to this 4th power and stuff like that. When you pinch off the flow, though, the story just changes completely. Now, the pressure difference in the hose from the water company to right there where before my finger, that pressure difference becomes very small. But that's okay because we're making the water go very slowly. We don't need to deliver very much water. So the water moves very slowly through the plumbing, loses actually very little of its energy because it's not rubbing very hard overall, and it shows up right behind my finger at almost the full pressure provided by the water company. Then it goes through the nozzle that I'm making with my finger and sprays out at high speed. All right, we'll call it a day and continue on Monday.